A groundbreaking discovery by the James Webb Space Telescope has left the scientific world in awe, potentially marking one of the most significant findings in the history of astronomy. For the first time, what appears to be artificial, urban-like light signals have been detected from space, emanating from Proxima Centauri b, an exoplanet orbiting the star closest to our own solar system. Located approximately 7 billion kilometers from Earth, this unprecedented detection has ignited fierce debate about the possibility of an advanced alien civilization existing beyond our world. Could these lights be evidence of life beyond Earth, or do they have a natural explanation? This discovery stands as a testament to the technological advancements we have achieved in recent decades. For years, scientists have gazed at the stars, hoping for even the faintest signal that might suggest we are not alone in the universe. Yet, despite decades of space exploration, we have mostly encountered planets with extreme environments, hostile atmospheres, and barren landscapes. Now, the detection of structured, seemingly artificial lights on Proxima Centauri b has turned that narrative on its head. If confirmed, this would represent not just an extraordinary scientific breakthrough but a profound philosophical shift, as it could mean that life, perhaps even intelligent life, exists beyond Earth. The urban lights phenomenon, evidence of alien cities? The phenomenon of the urban-like lights detected on Proxima Centauri b is not just intriguing, it is baffling. These lights differ from anything we have previously observed on distant planets. Natural planetary phenomena, such as volcanic activity, auroras, or reflected sunlight, typically produce diffuse, irregular patterns of light. However, these lights are distinct, they appear organized, structured, and highly localized, reminiscent of the artificial lighting found in human cities. What makes this even more perplexing is that the lights are consistently detected on the planet's night side, far from the influence of direct starlight, which suggests an artificial origin. The implications of this are staggering. If these lights are indeed artificial, it suggests the presence of a highly advanced civilization capable of constructing and maintaining large-scale infrastructure, potentially similar to or even surpassing the technological capabilities of humanity. The lights could be produced by vast energy grids, possibly powered by solar energy harvested during the day and stored for night use. This would imply that the civilization on Proxima Centauri b has developed sophisticated energy management systems, potentially far more advanced than our own. Alternatively, the lights could be the result of industrial or communication processes, signaling the presence of technology we can only begin to imagine. The intensity and regularity of the lights have led some scientists to speculate about the level of technological advancement required to sustain such a system. Could this be evidence of a Type 1 or even a Type 2 civilization on the Kardashev scale, capable of harnessing energy on a planetary or stellar level? While we can only hypothesize at this stage, the very possibility opens the door to entirely new ways of thinking about life and civilization in the universe. David Kipping's analysis, unusual thermal behavior. David Kipping, an astronomer at Columbia University, has provided critical insights into the peculiar thermal behavior observed on Proxima Centauri b. Typically, rocky planets absorb energy from their parent stars and re-emit it as infrared radiation. However, Proxima Centauri b exhibits a unique thermal signature that deviates from this norm. The planet seems to retain heat in an unusual manner, suggesting that there may be more at play than simple natural processes. This anomaly could be explained by the presence of artificial structures or energy grids designed to regulate the planet's climate. Kipping theorizes that these artificial systems could be responsible for managing the planet's energy distribution, allowing it to maintain stable temperatures despite the dramatic differences between its day and night sides. This would be a remarkable feat of engineering, indicating that any potential inhabitants of Proxima Centauri b have developed a deep understanding of their environment and the ability to manipulate it to suit their needs. This hypothesis aligns with the detection of the structured lights on the planet's surface, further suggesting that an advanced civilization could be responsible for both the thermal anomalies and the artificial illumination. The James Webb Space Telescope has played a crucial role in uncovering these anomalies, thanks to its exceptional infrared capabilities. By focusing on the infrared spectrum, which is less affected by stellar glare and cosmic dust, the telescope has been able to detect subtle thermal variations on Proxima Centauri b that would otherwise go unnoticed. The ability to observe these variations in such detail has provided scientists with invaluable data, allowing them to explore the possibility of artificial interventions on the planet. A planet divided, energy systems and climate control? One of the most intriguing aspects of Proxima Centauri b is the stark contrast between its day and night sides. The planet is tidally locked, meaning that one side is always facing its star, bathed in perpetual daylight, while the other side remains in constant darkness. Despite this, the night side appears to be illuminated by the mysterious urban-like lights, raising the question of how such lighting could be maintained in the absence of sunlight. Could this be evidence of a highly advanced energy system, capable of storing solar energy collected on the day side and distributing it across the planet to power artificial structures during the night? The concept of planetary-scale energy systems is not entirely far-fetched. On Earth, we are already developing technologies that harness renewable energy and distribute it through vast power grids. However, the systems potentially in place on Proxima Centauri b would be far more sophisticated. If the lights are indeed artificial, they could be part of an interconnected energy grid that spans the entire planet, drawing energy from solar panels on the day side and using it to power cities or other infrastructure on the night side. Moreover, the ability to regulate the planet's temperature across such extreme conditions would require advanced climate control systems. Proxima Centauri b's night side experiences frigid temperatures due to the absence of direct sunlight, yet the presence of these lights suggests that some form of thermal management may be at play. This raises the possibility that the inhabitants of the planet have developed technologies capable of controlling their environment, ensuring that their cities remain habitable despite the harsh conditions. Next steps: probing the atmosphere for life-supporting gases. While the discovery of these lights is compelling, it is not definitive proof of life. To determine whether Proxima Centauri b can support life, or if life already exists there, scientists must now turn their attention to the planet's atmosphere. The composition of a planet's atmosphere can reveal a great deal about its potential habitability. By analyzing the light that passes through Proxima Centauri b's atmosphere, scientists can detect the presence of gases such as oxygen, methane, and water vapor, molecules that are essential for life as we know it. Methane, in particular, is a crucial target for researchers. On Earth, methane is produced by both biological and geological processes, but its presence in significant concentrations is often linked to microbial life. If methane is detected in Proxima Centauri b's atmosphere, it could be a strong indicator of biological activity. However, scientists must be cautious, as methane can also be produced by volcanic activity or other non-biological processes. Distinguishing between these sources will require careful analysis of the planet's atmospheric chemistry. Oxygen is another key indicator of life, as it is a byproduct of photosynthesis and other biological processes. However, detecting oxygen on distant exoplanets is notoriously difficult. Oxygen is a highly reactive gas, meaning that it tends to bind with other elements and disappear from the atmosphere unless it is constantly replenished by living organisms. The James Webb Space Telescope is capable of detecting some atmospheric components, but its ability to observe oxygen is limited. Instead, scientists will look for secondary markers such as ozone, which forms when oxygen interacts with ultraviolet light. The detection of ozone would provide indirect evidence of oxygen, and by extension, life. The future of exploration, beyond the JWST. Despite its remarkable capabilities, the James Webb Space Telescope has its limitations. While it has provided groundbreaking data on Proxima Centauri b, it can only observe planets that are relatively close to Earth. Many potentially habitable worlds remain beyond its reach, waiting to be explored by future generations of telescopes. To overcome this, astronomers are eagerly anticipating the development of new observational tools, such as the Extremely Large Telescope, ELT, which is scheduled to become operational in 2028. The ELT will revolutionize our ability to study distant exoplanets. With its massive mirror and cutting-edge technology, it will be able to observe planets in unprecedented detail, reducing the glare from their host stars and allowing scientists to detect faint light reflections from their surfaces. This will provide invaluable information about the composition of exoplanet atmospheres, surface features, and even potential signs of artificial structures. By the late 2020s, the ELT and other next-generation telescopes could be the key to confirming whether the lights on Proxima Centauri b are truly artificial or simply a natural phenomenon. Future space telescopes will also be equipped with instruments specifically designed to block out starlight, enabling them to study the faint, reflected light from exoplanets with greater precision. These telescopes will be capable of observing the atmospheres of distant worlds in exquisite detail, potentially revealing signs of life or advanced technology. By reducing the interference caused by the intense brightness of host stars, scientists will be able to focus on the planets themselves, uncovering their secrets with a level of clarity that was once unimaginable.